Me? Yes, no, maybe so.
Yeah. Yep.
Okay. So today we're going to focus on alcohol oxidations, and I hope you all had a chance to download the slides to annotate them as we go. Okay, so what are we learning today? So first, we're going to start off with learning how to assign oxidation numbers. I know you guys did a little bit of that in general chemistry, but it's done a little bit differently with organics. And so once we get through that, we'll start looking at some alcohol oxidation reactions, first starting with just classifying alcohols. And then we'll look at the primary alcohol oxidations, and then the secondary alcohol oxidations, and the tertiary alcohol oxidations. Okay. So what is oxidation and reduction? And so if we'll remember from 2017, 2080, right, oxidation, reduction, or redox reactions are reactions that involve the transfer of electrons between species, right? And it's going to be different from other types of reactions. It'll be different from these non-redox reactions because for everything that's going to be oxidized, there's going to be something that's going to be reduced in equal magnitude. And so let's just kind of put in our mnemonics for the easiest way to remember these redox reactions. So we've got oil rig, right? OL, oxidation is going to be equal to loss of electrons, whereas reduction is going to equal the gain of electrons in our species. Right, so that's one mnemonic, and then the other one, if I know how to count, Leo the lion says her. Right, once again, we have oxidation is equal to the loss of electrons, reduction is equal to the gain of electrons. So that's pretty simple and straightforward. So we're now going to be moving into reactions where one species is reduced and another is oxidized, right? The definition of a redox reaction. And so the fastest way to kind of figure out which species is being oxidized or reduced is to use what we call oxidation numbers for the products and the reactants. And this is going to be kind of a three-step bookkeeping process that focuses on individual carbon atoms involved in the process. So let's take a look at the steps. So for the first step, right, we have assign oxidation levels to each carbon that changes from the reactant to the product. And so within that, for the very first thing, for every bond from carbon to a less electronegative atom, and for every negative charge on the carbon, we're going to assign that carbon a -1 charge. So if we had, say, a carbon to a hydrogen bond, right? Hydrogen is going to be less electronegative than carbon. And so this carbon, for every single hydrogen that's attached to it, it'll have a -1 kind of formal charge on top, or oxidation charge on top of it. So I hope that makes sense. So let's move on to the second kind of criteria. And so for every bond from carbon to another carbon atom, and for every unpaired electron on the carbon, we're going to assign a 0. So if we had something like carbon-carbon bond, right, both of these are going to be 0s. Even a carbon-carbon triple bond, we're still going to have a 0 on those carbons. And so our next criteria is that for every bond from carbon to a more electronegative atom, and for every positive charge on the carbon, we're going to assign a +1 charge on that carbon. So if we had something like a carbon to a nitrogen, or a carbon to an oxygen, right, we're going to give that carbon a +1, and then the nitrogen or the oxygen will get that -1. And then once we've done all of that, those first three things, we're going to just add up all the above numbers to obtain the oxidation level of that specific carbon. So let's say we had this carbon-carbon bond. We also had a hydrogen attached to it. And we had, so if we're going to focus on this center carbon, bond that it has to another carbon, that's going to count for 0. This bond that it has to this nitrogen is going to count for 1. It has a bond to a hydrogen, which is going to account for a -1, and then another bond to a hydrogen, which is going to account for another -1. And so we would just add all of that up to get the oxidation level of that specific carbon. Are there any questions on that? Okay. So then the second step, if you have some kind of reaction and you're trying to determine how much oxidation or how much reduction happened from your reactant to your product, you're going to start looking at the oxidation numbers of the reactants and products, and you're going to add within each compound the oxidation numbers of all the carbons that you kind of consider the ones that we focused on in step 1. And you're only going to consider the carbons that undergo a change in the reaction. And if that's confusing right now, we'll do a practice problem in about 2 slides to kind of address that. And so then the final step in assigning oxidation numbers is that we're going to find that difference between the oxidation number of our products and the oxidation number of our reactants to determine whether the transformation was an oxidation, reduction, or neither. Right? And if that difference was a positive number, that's going to be an oxidation by whatever that number is. So if we had a 4 electron difference, it's going to be a 4 electron oxidation. And so if that difference is a negative number, it's going to be a reduction. And if that difference is a 0, it's going to be neither. So let's kind of put all of that together. Let's say we had ethanol, H3C, CH2OH. And let's say we treat it with a chromium 6 compound. Don't worry too much about the chromium just yet. 2SO4, aqueous. And what we're going to get is acetic acid, H3C, C, oxygen, and a carboxylic group on the end. So now I want you guys to take just a minute and tell me what type of reaction this is. Is this an oxidation, a reduction, or neither?
Would it be a reduction?
Close. It's going to actually be an oxidation. And so let's see, and specifically a 4 electron oxidation. And so let's see how we kind of get to that. So the carbon that's going to be changing between our kind of our reactants to our products is going to be this carbon right here, right? And so let's try to calculate what the oxidation number of that carbon is between the reactants and the products. And so this carbon is connected to 2 hydrogens, right? And so those 2 hydrogens are going to give it each a -1 oxidation. And then it's connected to an oxygen, right? And that's going to give it a +1 oxidation. right? And then it's connected to another carbon, which is just going to have no influence on it. So when we add all of that together, we get -2 plus 1, which is going to get us -1 for the oxidation number on our reactant side. And then let's do the same thing for our products, right? So it has two, you can kind of think of the double bond to the oxygen as two bonds to oxygen. And so each one of these is going to cause that carbon to get 2 plus 1s, right? Because oxygen is more electronegative than that oxygen. So we'll do 2 plus 1s, and then it has another bond to an oxygen. And so that's going to be another +1. And then this bond to a carbon just doesn't matter in our case. So that's just going to be a +0. And then our change is going to be 3. And then when we do kind of the difference between the products and the reactants, we're going to do our 3 minus -1, which is going to give us a 4. And so since that difference is a positive number, we're looking at a 4-electron oxidation. So ethanol is being oxidized to get us to this acetic acid. Are there any questions on that? Okay. So let's do a couple practice problems with kind of assigning these oxidation numbers. And so let's draw out a methane, methanol, oh, not methanol, that is going to be ethane. And then let's do the last one, carbon, hydrogen, hydrogen. All right, I'm gonna give you guys about a minute to kind of work through that. Actually, let me toss in this last one. Carbon tetrachloride. And I guess I didn't make it clear, but we're going to focus on the oxidation number of the underlined carbon.
Are we supposed to say the answers? Like,
Yeah, you can unmute and yell the answers.
I guess I'll do the first one. Is it -4?
Yes, it is. Exactly, right? We've got 4 -1s from each of the hydrogens. All right. Does anyone want to do the bottom left?
-3.
Yep, exactly. Okay, what about the top right?
-2.
Mm-hmm. And then what about the bottom right?
+4.
Yeah. So it seems like you guys are comfortable with assigning oxidation numbers. And so it's kind of important to note that this is just a formalism or a bookkeeping kind of idea. So the kind of charges that we're putting on the carbons isn't real. And so the oxidation state formalism is just a way to help us keep track of where our electrons are going in our redox reactions. And this is going to come in handy for kind of the next reactions that we're going to be focusing on, which is the alcohol oxidation reactions. And so what are alcohols? Right? They're compounds in which one or more hydrogen atoms in an alkane have been replaced by an alcohol or an OH group. And so these alcohols are going to fall into kind of different classes depending on how the alcohol group is positioned on the carbon atom. And it's important to note that these alcohol oxidation reactions, what they're going to do is that they're going to create carbonyl compounds. Using what is known as a chromium 6 reagent, typically. Okay, so I said that we can classify these alcohols, and the first way to classify them, or the main way to classify them, is into primary, secondary, and tertiary alcohols. And you guys can have heard kind of those ideas before, so let's look briefly at what primary alcohols are. And so something like ethanol would be a primary alcohol, right? We've got this OH group, and the carbon that it is attached to is only attached to one alkyl group, this methyl group. We also have propene-1-ol. Don't worry too much about the names yet. And so once again, this OH group is attached to a carbon that's attached to just one other carbon. And then the last example that we have is going to be this. And so once again, this is the alcohol group, and this carbon that it is attached to is attached directly to only one other carbon. And so the exception to this rule is methanol, which looks like this. And this is going to be classified as a primary alcohol, even though the carbon that it is attached to isn't attached to any other alkyl groups. Okay, so that was primary alcohols. So the next kind of classification is secondary alcohols, or where the OH group is going to be attached to a carbon atom that is attached to two alkyl groups. And so some examples of that, we have propene-2-ol. And so this is our alcohol group. This is the carbon it's attached to, which is attached to two other alkyl groups. We'll do another example, H3C, H2, CH3. This is butane-2-ol. And then our OH group is right here. And the carbon that it is attached to two other alkyl groups. And so our last kind of class of alcohols is going to be our tertiary alcohols, where the carbon atom that is attaching to the OH group is going to only be attached to three alkyl groups. And so this is what it's going to look like. If you guys remember, right, this is just going to be the conjugate acid of our tert butoxide that we use in our E2 reactions. And then this is another example of these tertiary alcohols. Right? And so the carbon that it's attached to is attached to three other alkyl groups. And so let's try a practice. So I want you guys to take a minute to just classify these alcohols. And then just yell it out when you're done. Does anyone want to yell out the answer for the first one?
Secondary.
Mm-hmm. Exactly. Anyone want to do the second one?
Secondary.
Any takers for the second one?
Secondary.
Someone said secondary. Can you not hear us?
Okay, what about the third one?
Corel, can you hear people talking?
Any ideas, any thoughts? Okay, so this second one is also going to be a secondary alcohol, right? The OH group is right here. And then the carbon that it is attached to one other carbon and another carbon right there. So a secondary alcohol. This one, let's see what we figure out, right? This is the carbon that OH group is attached to. And then that carbon is going to be attached to one other carbon right here, another carbon right there, and our third carbon right there. So this is going to be a tertiary alcohol. And then this one, right? This is the OH group that we're focusing on. And then the carbon that it is attached to is right here. And that carbon is going to be attached to only one other carbon group right there. So this is going to be a primary alcohol. And it's going to be important to be able to classify these alcohols when we move into the reactions of these alcohols. And so are there any questions on this? Okay. Without further ado, I will stop sharing.
Can everyone hear me?
Yes.
Yes. Okay, good. Okay. So now we're going to get into the reactions of alcohols and the oxidations of alcohols. All right. So we're going to start by focusing on primary alcohols. And so the common reagents that you'll see with the reaction to primary alcohols is, to start off with, we're going to talk about, we have Kr2, Cr2O7, Na2, Cr2O7, CrO3, or you could have KMnO4 with a base, or H2CrO4. All right, so these are possible reagents. All will get you to the same place. Okay, and so when these reactants are used in an aqueous environment with an acid, a primary alcohol will be oxidized first to an aldehyde, which can't be stopped there. So even though you're going to create this aldehyde to start, you're unable to prevent the further oxidation. And so after the aldehyde forms, the next stage is the aldehyde will be turned into a carboxylic acid. Okay, so if we look at this molecule right here, we have a primary alcohol. And if we react this with Kr2, Cr2O7 with H2SO4, we're gonna first get our aldehyde like this, okay? And so this is the first stage where the aldehyde forms, but this right here, we can't isolate, okay? So it's still in solution with Kr2, Cr2O7 and H2SO4. And so the final stage of the oxidation is turning this into a carboxylic acid. Like that. Okay, and so any of these reactants that I wrote down above will get you to this final carboxylic acid in the reaction with your acid. Okay. Sure.
How did you know an aldehyde was gonna form, like the thing in the middle?
Yeah, so I would say for the purposes of this course, don't worry about it. That goes for like most of these, like all the reactions we'll talk about today. You'll just want to know like the products that form. You'll get into more mechanisms and stuff like that in 3580 in the second semester. So yeah, we're not going to be showing you the mechanism for these reactions. So just know that that's basically a thing that happens in aldehyde forms, but you can't isolate it using these reactants.
So we just memorize it for now?
Yep. Exactly.
I have a question.
Mm-hmm.
So for the first three, there is a chromium and then some sort of oxygen. So for the first two, is the Kr and Na, are they spectators? And then it's only the chromium and the oxygen that react?
I believe that's the case.
Okay, and then for the, oh, sorry, go ahead.
No, go ahead.
And for the last one, why do you have to react it with a base instead of a strong acid?
Again, so like this will get into more like mechanistically, and will require a more mechanistic explanation as to how the base comes into play versus the acid. So I would say, like, again, don't worry about that too much. Just know that if you decide to go with that reactant, you'll need to pair it with a base instead of an acid.
Okay, thank you.
Sure. Any other questions? Okay. So if we look further at reaction to primary alcohols, right? So water promotes the transformation of aldehydes into the carboxylic acid because they're basically in equilibria as the hydrates form. And so, yeah, so the hydrates form by the addition of water across the C double O double bonded to the oxygen bond. Okay, so we have our aldehyde right here, and this is in equilibrium with this. So this gets a little bit to some of the questions you're asking, but still doesn't exactly show how it happens. But this is your aldehyde hydrate right here. Which is in equilibrium. And so adding the chromium 6 in whichever form shown previously is going to get you to your carboxylic acid. Okay, so aldehyde hydrates are basically just alcohols, and therefore they can be oxidized like secondary alcohols. But because of the absence of water in anhydrous reagents like PCC, which we're going to talk about in a minute, a hydrate doesn't form, and the reaction is going to stop at the aldehyde. Okay, so this is going to make more sense in a second. Okay, so still looking at primary alcohols, except we're going to be taking a look at a new reagent. Okay, so this one we're going to call PCC, which stands for pyridinium chlorochromate, which is basically this complex right here. Okay, so this complex right here is PCC. And you may also see something called DMP used. And DMP is a fairly complex molecule, which I won't be drawing out, but it'll accomplish the same goals as PCC, okay? And so when we react this primary alcohol with PCC in dichloromethane as the solvent, we are going to get an aldehyde. Like this. Okay, so by using PCC, we do not form the hydrate. And so we're able to stop the reaction at the aldehyde, okay? And so we're able to isolate the aldehyde and it won't continue on to forming a carboxylic acid. Knowing the difference between the two reagents that we've talked about, or the two types of reagents that we've talked about so far, are important in synthesis problems. And so you'll probably find those useful there, okay? So now we're going to move on to reactions of secondary and tertiary alcohols. So for the reactions of secondary alcohols are oxidized to a ketone in aqueous acid. And so it's going to be oxidized to a ketone in all instances. It doesn't matter whether you use PCC or the other chromate molecules that we talked about. Okay, so if we have something like all right, so we have a secondary alcohol here. This is going to form a ketone like this. Okay, and so again, this will happen whether we use the K2CO2O7, the Na2CO2O7, or any of those things. You're still going to get a ketone. And finally, for tertiary alcohols can't be oxidized under normal conditions because they lack the CH bonds at the alpha carbon that are needed, that must be broken in the mechanisms and are required to oxidize. So tertiary alcohols will not be oxidized. Are there any questions on anything so far? Okay. And so just want to add a quick note, right? And so we can differentiate between weak oxidants and strong oxidants. Okay, so weak oxidants will only oxidize primary alcohols to aldehydes. And strong oxidants will oxidize primary alcohols to carboxylic acids. And secondary alcohols are oxidized to ketones regardless of whether it's a weak or strong oxidant. And tertiary alcohols will not be oxidized by these reactions at all. Okay, so now let's try some practice problems. So for these problems, we're going to treat this compound right here with each of the reagents shown below. Okay, so that's going to be your reactant, your substrate for each of the following reactions. So I'll give you a few minutes to try these, and then we will talk about them. Okay, so let's take a look at the first one. So for the first reaction, we're reacting that main molecule with KMNO4 with NaOH at room temperature, and then secondly, H3O plus. Okay, so can anyone describe to me, or first let's look at this reactant, right? So what type of alcohol is this one? Primary, secondary, tertiary?
Tertiary.
Tertiary. Good. And how about this one?
Secondary.
Good. And lastly?
Primary.
Good. All right, so we have a primary, secondary, and tertiary alcohol all in the same molecule. So if we react this molecule with KMNO4, NaOH, and then the H3O plus, let's just go. So what should happen to the alcohol that was on that carbon on the corner over here? Will it become a carboxylic acid, ketone, or neither?
It would turn into a ketone.
Good. So we get a ketone over here. And how about the primary alcohol? What does the primary alcohol turn into?
Aldehyde?
Close. So what is KMNO4? Is KMNO4 a weak oxidant or a strong oxidant?
Strong?
Strong. So the primary alcohol should turn into
Carboxylic acid?
exactly. And how about our tertiary alcohol? Should that be ketone, carboxylic acid, or neither?
Neither.
Good. So that'll stay the same. All right. How about DMP with dichloromethane as our solvent? How about we look at our primary alcohol first?
It would turn into an aldehyde.
Good. Yep. So DMP is considered a weak oxidant. And how about our secondary alcohol?
A ketone.
Good. And then our tertiary alcohol, again, is unreactive. All right. How about CrO3? Let's start with our primary alcohol.
What was
CR,
the carbox? Oh, wait. Oh, okay, I'll go. I thought it was the carboxylic acid, right?
Good. Yep.
Yes.
Yep. CrO3 is going to be another example of a strong oxidant. And how about at our secondary alcohol?
Ketone.
Yep.
Wait, I have a question, real quick.
Yep.
So does the secondary always form a ketone no matter like the strength of the? That's what okay, that's what you're saying before. Okay.
Yep.
Yeah.
Yep. So secondary will always form a ketone, whether you're using strong or weak oxidant. Exactly. Good. All right. And finally, is Na2CO2O7 a strong or weak oxidant?
strong, so that would turn into carboxylic acid.
Good. Okay. And let's look at just a couple more practice problems. Okay, so for this one, you're going to predict the products. And so I'll give you a few more minutes to work through these, and then we will talk about them. Okay, let's take a look at the first one. So we'll say this is the first one. So is this a primary, secondary, tertiary alcohol?
Primary.
Primary, good. And is PCC a strong or weak oxidant?
Weak.
Weak, good. So our product should be what? Which does this alcohol turn into?
An aldehyde.
Good. Okay. And let's look at this one. So we same substrate. So we know it's a primary alcohol. And is CrO3 a strong or weak oxidant?
Strong.
Strong. And so it should produce what?
Carboxylic acid.
Good. Okay. And finally, let's look at this one. So from left to right, what is the first alcohol?
Primary.
Good. And how about the second one?
Secondary.
Mm-hmm. And the third one?
Secondary.
And lastly?
Tertiary.
Good. Okay. And again, is PCC a strong or weak oxidant?
Weak.
Weak. And so our primary alcohol should turn into what?
An aldehyde.
Aldehyde. And our secondary alcohol should be
Ketone.
and our tertiary.
Stays the same.
Good. Okay. So that's all I have for you content wise. Are there any questions on any of these reactions or anything like that?
Oh, I just have one quick one.
Sure.
So like when you use a strong oxidant, you need like at least some type of acid.
Mm-hmm. Yeah. So most commonly you can just use like generic H3O plus or H2SO4 is common too.
Okay.
Mhm.
Thank you.
Yep.
Can you possibly go over like how we can identify if something's a weak or strong oxidant again?
Yeah. So basically this is just going to come down to memorization, right? So our strong oxidants are going to be Kr2, Cr2O7, Na2, Cr2O7, KMNO4, CrO3, H2CrO4. Yeah, so these are going to be your strong oxidants. And then your weak oxidants, you're going to have PCC or DMP.
Thank you.
No problem.
If you paired the strong oxidants with a weak acid, would the reaction just not occur, or would it occur at a slower rate?
That's a good question, and I'm not sure of the answer, but I can look into it. Yeah, because I'm not exactly sure. Corel, I'm not sure if you know, but
I do not.
yeah. Okay, so yeah, we can find that answer for you because that's a good question.
Thank you.
Sure. Any other questions for either myself or Carell?
Yeah, so when Carell went over that slide on assigning oxidation numbers, do you mind showing that slide?
Yeah, let me pull it up really quickly. Sorry, let me find it again. There it is. Okay. Assigning oxidation numbers. This one?
Yes.
Oh, did you want me to go over it?
I actually have a question about your slide on assigning oxidation numbers, step 1. Do you mind going to that slide?
There we go.
When you have the +1 at the bottom left
Mhm.
on the C,
Mhm.
what's that referring to?
Oh, so that's going to refer to like if I have it, the carbon, if I have it attached to a less or more electronegative atom. So like when I have carbon and nitrogen, because nitrogen is more electronegative, that's going to get the -1, and then the carbon's going to get the +1.
Okay. So when you're determining the oxidation number, how would you do that?
Yeah. So you would look at, well, let me actually go to this example. Okay. So let me just go through a different example. So if
Okay.
what?
Oh, I said okay.
Okay. So if I have something like this, right? I'm going to first look at what things I have attached to this carbon, if that's the carbon I'm focusing on, right? And so first I'm going to pay attention to this carbon-hydrogen bond. And because hydrogen is less electronegative than carbon, right? This hydrogen is going to get the +1 and carbon